Good morning, and I want to thank everybody for coming out this morning and for inviting me to come out this morning. It's quite an honor and quite a thrill to be here, and it's actually particularly fun to follow Jane and Dave and to pick up their story. I came in later to their story after they had already made the discoveries. I became interested in this region because I had learned about it from them, and what was interesting to me about this region of the solar system was not just the stories that they could tell by finding these objects and seeing where the objects were going, but the objects themselves were potentially very interesting. As Dave mentioned, these are the repositories of ices and materials that have been in the solar system in deep freeze for 4.5 billion years, and we hadn't had many ways to study them in the past. The difficulty, though, was that these objects were incredibly far away and incredibly faint and almost impossible to study. If you looked at the sizes of the objects, you notice that most of the information that you saw in the last two talks were about the locations, the orbits of the objects, what they did, but not much about what they were. And that's because if you looked at the size of the objects and you wanted to learn something about the object itself, you would realize that the objects were generally tiny. Other than Pluto, which is, as Jane mentioned, is part of this overall population, other than Pluto, the biggest objects you can sort of see hiding in through there, these are the biggest ones that were known by about a decade ago. And I give them pretty colors, but other than the colors, we really didn't know anything about these things. If you wanted to learn about the objects themselves and what they were like, you really had only one option. That was to go study Pluto and its moons and its atmosphere and its history. There were rich stories that you could learn from studying Pluto. Pluto contained a little bit of the record of the history of the solar system. But even though it was part of this population, one of the reasons why people still considered it at the time a singular object and still talked about it as a planet even in 2001 is because it really was the only large object that we knew anything about. So in about 2001, a little bit earlier than that, I was generally frustrated with the difficulty of studying these faint objects, and I decided the solution was to go find brighter ones so we could study them in more detail. And the way we do it is very similar stories to what you heard from Jane and Dave. Larger telescopes, larger CCD arrays, surveys of now instead of using largest telescopes to look at small areas of the sky for the faint objects, we used smaller telescopes. We eventually, over the last 10 years, have now covered the entire sky, both the northern and southern hemisphere, looking for the very brightest objects out there. They're harder to find because there are only a few. There are a handful, and you don't know where to look. You have to end up looking across the whole sky to find them. But over the last decade, we've been able to go from Pluto being the only singular object out there to a collection of 100 objects that are large enough to study in detail, including these. These are the largest ones that we found in our survey. Eris is a tiny bit bigger, or perhaps just around the same size as Pluto. The rest of these are a little smaller than Pluto. And each one of them, like Pluto, has been able to be studied in detail to learn a little bit about the history of the outer solar system. And what's been very fun is that each time we found one of these new ones, we would, of course, rush off to whatever telescope we could get, often on Mauna Kea, like you saw from Jane and Dave. And we would quick study it in every way we could. And each time, these new objects contained a different story. It wasn't that we found an object and, yeah, the story was kind of the same as Pluto's story or the same as the last story. Every one was different, and it took this collection of sort of 8 to 10 large ones before we started to be able to see the connections being able to be put together. So I'm going to tell you today about just some of these tales that we have learned by looking at these objects in the outer solar system. And each one of these objects I can talk about for hours at a time. We've learned so much. And I'm not going to do that. I'm happy to report. So I had to. This is a very hard thing to do. I had to pick a few of my favorites. It's like saying that you have a favorite child. I only have one child, so it makes it easier for me. But these, I'm gonna pick three, and I debated back and forth and changed which ones. But I'm gonna first talk about Haumea, because Haumea is, I would say, it is safe to call Haumea the strangest object in the outer solar system. We knew that it was strange very early on after discovering it because we realized that it was It's elongated. It's about twice as long in this direction as it is in this direction. It's elongated and it's rotating very quickly. It rotates once every 4 hours. It's the fastest rotating large object in the entire solar system, not just the outer solar system, the entire solar system, fastest rotating large object out there. Very, very strange object, rotating end over end. And we learned this part early, and we were scratching our heads trying to understand why something would be rotating quite so quickly and why it was so elongated. Realized that the elongation, of course, makes sense. If you rotate something that quickly, it will become elongated. But what we could do is use the amount of elongation that it had to actually measure something about the interior that you don't see, the density of the object. If it were more dense, it actually sort of counterintuitively, it would elongate more. If it were less dense, it would elongate less. And from the amount of elongation, we could tell that it had a density of 2.6 grams per centimeter cubed. Now, 2.6 grams per centimeter cubed actually is an important number. Up until that moment, every large object in the outer solar system was thought to have a density of precisely 2.0000, or something like that. Pluto has a density of 2. Triton, Neptune's large satellite, thought to be a captured Kuiper Belt object, has a density of 2. A density of 2 means that you have about 70% rock on the inside, about 30% ice on the outside. And that was what people assumed was a typical value. So a density of 2.6 means that you have almost all rock and just a little bit of ice. Strangely, though, if you look at Haumea spectroscopically, and this is one of the main tools that we use to understand these objects. As soon as we found them, we would go to a telescope, take a spectrum, which is looking at the reflected sunlight coming off of the body, and in that reflected sunlight, the fingerprints of whatever chemicals are on the surface appear. And in this case, this was quite a big surprise to us, because most of the time when we looked at the spectra of the objects, they looked, instead of like this big complicated thing, they looked sort of like a line straight across here with a lot of noise on it. They looked like nothing. Astronomers love to classify things, and so we called these type B spectra for boring, because there was nothing going on. And this one, we took this first spectrum and almost fell out of our chairs, because it has these very deep absorptions in the reflectance spectrum, and the very deep absorptions are due to frozen water. Maybe that doesn't sound very surprising, but we had never seen this much almost pure frozen water on any object in the outer solar system. This solid line is actually a spectrum of a laboratory model of pure water ice, and the dots are the actual spectra from the telescopes. And this was some of the most pure water ice we'd seen anywhere in the outer solar system. It's pretty strange to find pure water ice on an object with a density of 2.6. Of course, ice has a density of 1, so we were a little surprised, but we realized that it must mean that this object looks something like this. Rock on the inside, like this, and just a little bit of ice. This is the actual scale of how much ice and how much rock must be on that object. A very strange-looking object, sort of reminds me of an M&M that you don't want to eat because it's rocky on the inside. How would this form? Well, we're slowly getting these observations, trying to put these stories together, and the story that we came up with is the reason that Haumea is so strange, that it has ice on the outside, such a high density, such a rapid rotation, is that earlier in the history of the solar system, it was a larger object, and it got hit, oblique blow, by another large object. That oblique blow made it start spinning. It also first cracked open an icy mantle of material, flung that material out into the solar system, left just a little bit of ice on the outside, made it spin rapidly and elongate it. And we were pretty happy with that idea, and we wrote a paper describing it, and the people who calculate theoretically how frequently that should happen said, no chance. This is, probability is 1 in a billion that this would ever happen. So we said, okay, fine. But there were some other strange things about Haumea. One of the strange things is, here's a nice picture of Haumea from the Hubble Space Telescope. Haumea has not just one moon around it. A lot of objects in the Kuiper Belt have one moon on it. Haumea actually has 2 moons going around it. And those 2 moons, if you take spectra, like the spectrum I showed you of Haumea, if you take spectra of those 2 moons are just as icy as Haumea, which is very strange. We hadn't found any objects like that in the outer solar system, and here suddenly we have an entire little family. And we said, hey, it actually makes sense if you have this, I'll say giant impact, comes in, hits obliquely, makes it spin, and two of the chunks go into orbit around it. Kind of makes sense. And the theorist said, no, that's only one chance in 10,000. And then as we continued studying other objects in the outer solar system, the rest of this story really came together, I'd say, beautifully, which is that we were looking at other objects in the outer solar system, taking spectra. Again, spectroscopy is a very important tool out here. And as I said, most of these were these type B spectra. And all of these dark dots are objects that we took spectra of the type B spectra. This is a plot just like the ones Dave was showing you. Here's distance away from the sun on this side. Here is how elongated the orbit is up here, and I'm also showing you how inclined it is to the plane of the planets down here. These are the same objects. And you can see most of these type B boring dark objects are scattered throughout the Kuiper belt. These white dots are a very small subset that we started finding that had these pure water ice surfaces just like Haumea. It was quite a surprise every time we found one. And we scratched our heads until we made this plot and realized they're all in essentially the same place in orbital space. They're not close together in the sky at all. Otherwise, we would have probably recognized them very quickly. But they have similar orbits, though they're all around each other in the sky. Why is this the case? Well, at this point, it was an almost obvious explanation and an analogy from the asteroid belt. When you have a giant impact in the outer solar system and you break apart an icy mantle of material and fling stuff into the solar system, your main object stays in the middle, but all those other little objects move away just a little bit, and they end up on orbits that are very similar. These are the icy chunks of orbits of materials that came from the mantle of Haumea. Let me show you how that works. If for example, you started out, these are the objects again, and here's just a little toy model where if you start everything in the center object right here and just eject it at very small velocities, 150 meters per second here, they go into this little cloud like this very characteristic looking cloud like this. 500 meters per second, if you want to include that one. You can always have one object that's an outlier and ignore it anyway, except of course that is Haumea itself as the only outlier in its whole family. So again, we had to scratch our heads. One of my graduate students came up with the beautiful explanation, which is if you take, I'm going to show just this small region of space right through here, and we did computer simulations where we just put test particles into the outer solar system in this region and watched what happens to them. Most of the time, in this region of the solar system, things don't move. They just stay in one place for 4.5 billion years. Occasionally, things move. So here, these points are the real objects, and it's about 1 billion years, and nothing happens. These don't move. This guy moves a little bit. Nothing moves, nothing moves, nothing moves, nothing moves, until you get to right here. If you put an object right here, it starts to oscillate up and down in eccentricity. It gets more elongated, less elongated, more elongated, less elongated. Eventually, these objects get up to here where they'll eventually cross the orbit of Neptune, and then they'll be ejected from the solar system, or they'll be injected into the solar system. And of course, this is Haumea. Haumea is right here. It had started out right here, and it found itself by chance, as far as we can tell, which seems strange. It found itself by chance in the 12 to 7 mean motion resonances. Dave talked about these much more common resonances, 3 to 2, 2 to 1. 12 to 7 means that Neptune goes around 12 times, Haumea goes around 7 times. And it's such an obscure resonance that no paper had ever been written about this resonance as far as we know. But it turns out that this resonance is perfectly timed so that after around 2 or 3 or 4 billion years, you will have oscillated up to here and almost been ejected from the solar system. So this really was, I think, the smoking gun that we really had found what we were looking for, this large impact in the outer solar system. And the theory ended up being so good that we could go back and predict other objects that were part of the family. Here were some, where are they? Somewhere in here. No, this next one. There we go. These guys, these two objects were objects that we hadn't looked at before, but they were within this cloud of stuff. And we went to the telescope and took spectra of them, and they too are these big icy objects too. So now we can actually very easily go and look at where objects are in orbital space and say, oh yeah, you're probably part of this, and go and get a spectrum of it, and sure enough, it looks like a big icy object. It's a very nice, well worked out theory. We now got to go back to the theorists and say, hey, look, it really did happen. And they say, oh yeah, that's about one of those should have happened in the solar system. But I say that sort of casually, but that evolution from 1 in a billion to 1 in 10,000 to 1 was an entire evolution in understanding the collisional history and the size distribution history of the outer solar system. That evolution occurred as we were kept on pressing this idea that this one major impact really happened. We now know that these sorts of impacts occurred not just for Haumea, which left a very dramatic signature, but we're pretty sure that it happened on Pluto, on Eris, all the guys with the small satellites, on Eris, on Kwarwar. Orcus, we're still on the fence about, but these giant impacts that were supposed to not have ever happened seem to be a relatively common occurrence, and that's changing our view of how the outer solar system really must have behaved. I'm going to switch to a new object now because I have to get a few in. Makimaki. All these names are a little bit crazy, but they're fun to come up. Makimaki is the creation god of the Rapa Nui from Easter Island. Makimaki was discovered right around Easter. We like that name. Makimaki was an interesting object. It is the brightest Kuiper Belt object known after Pluto, and so we can study it in very good detail. Once again, spectroscopy is one of the best ways for studying it, and after finding all those very, very boring flat spectra, we took a spectrum of Makimaki all the way from visible light out to the infrared here, and it's very rich in absorption features, and compared to Pluto, it looks almost identical. Those absorption features are almost all due to frozen methane on the surface of Pluto and frozen methane on the surface of Makimaki. But it's a little bit strange. They're not exactly identical, even though the features are all in the same places. You can see it best out through here. These features on Makimaki are broader. They're washed out. You can see it through here too. These three distinct fingers they're broadened and they almost blend together. In spectroscopy of ices, of solid state bodies, you broaden the spectrum by having the photons travel a long path length through the ice, through the mineral. So if you have only a very small path length of ice, you have a little bit of absorption that happens, and then the photons go back out. If you have a long path length, the photons can get absorbed, a lot of them, so the ones on the sides get absorbed too. So just that spectrum shows you not just that methane is on the surface, but that methane is in the form of large blocks of methane. It actually looks like slabs of methane that are compressed and have very few bubbles left inside of them. They sort of look like, actually, around here, you'll know what these look like. If you look at, when you see icebergs, the beautiful blue color of icebergs that look sort of unreal, they're so blue. And that's because the icebergs get compressed and all the bubbles get pushed out of the icebergs, and so the path length through the ice is very long, and so you get those absorptions that you wouldn't otherwise get from just the ice on the surface. You see those blue things. You can think of Makimaki as covered in big methane icebergs, except that doesn't make any sense, so don't think of that. So it was quite a shock to find something like this to begin with, but to see that it was so similar to Pluto and yet not really that similar at all was the bigger shock. And so we again, there was a lot of head scratching. So we were scratching our heads trying to understand why it happened. Makimaki is a little bit smaller than Pluto. It's a little bit further away, so it's a little bit colder. What could be going on? And we sat down and started writing a very simple computational model to understand how ices would evolve on these bodies. On these bodies, the main ices that you get on the surface that you would see that might be interesting are going to be methane and carbon monoxide and nitrogen. On Pluto, that little bitty shoulder right there is due to the dominant nitrogen ice. You don't even have to believe me, but that's nitrogen right there. We don't see it on Makimaki in better data here. So Makimaki looked like it had these big slabs of methane, no evidence for nitrogen, what was going on, and we realized that if you just considered these ices on the surface, and we know that the ices are on the surface, these ices evaporate, they become atmospheres. Atmospheres eventually get lost to space. You hold on to your atmosphere better if you're bigger, and you hold on to your atmosphere better if you're colder. When your atmosphere gets lost to space, more ice evaporates. Eventually, all of your ice is going to evaporate, and you're going to be left with one of these boring spectra. We put this computational model together and realized that it explains everything we knew about ices in the outer solar system that we had learned so far really quite well. And the way it works is this. These are the three main ices: methane, nitrogen, carbon monoxide. Any object, here are the objects, any object on this side of the plot can have the ices left over. Any objects on this side must have lost all of its ices to space. They've evaporated and gone away. And the ices behave slightly differently because they're different volatilities and different molecular weights. And Eris, the large one we had found, has methane on its surface. Triton and Pluto both have methane on their surface. Sedna, I'll talk about next, has methane on its surface. And there is Makimaki, where's Mach? Makimaki is 2005 FY9. And you can see it's right here in this region where it holds on to methane, but it's potentially lost its nitrogen, or almost lost all of its nitrogen. So we've caught a body in the process of losing its atmosphere. It's lost some of it. It's lost its main atmosphere, would have been a nitrogen atmosphere, and that's mostly gone. And what's left, because there's no nitrogen left, the methane is able to form into these huge slabs on the surface. In a short amount of time, short meaning about 1 billion years, the methane itself is going to slowly evaporate away, and this atmosphere is going to be lost too. What's interesting, though, is that it's not the only object in this region. Kwarwar, one of those other large objects, sits right here too, even a little bit this side of Makimaki. It's about the same temperature, that's this plot, but it's a little bit smaller, so it sits over here. So it has the possibility of having a little bit of methane left. We knew at the time, though, that the spectrum of Kwarwar was dominated by ice, by water ice. This looks similar to Haumea that you saw earlier. Big absorption here due to water ice. And so it didn't look like Makimaki at all. It looks like a big ice ball, more like Haumea. And yet, if you look at what ice should look something like this, and it doesn't fit out through here. So why doesn't it fit out through here? Well, the reason it doesn't fit out through there is because there is a little bit. Here's now a model where you add in a little bit of methane. I'll show you where the methane is. You add in a little bit of methane right here, and actually a little bit of ethane helps too, which is an expected irradiation product of methane. And there it is. That little dip right there is due to methane. These dips are due to methane. What you're seeing on Kwarwar is, I said Makimaki is an object in the process of losing its atmosphere. Kwarwar is an object that has essentially lost all of its atmosphere. It has a tiny bit of methane sitting on the surface, probably in little patches, probably close to the poles. It occasionally heats up, goes in the atmosphere, and is rapidly blown away. If we came back just a little bit later, this one really would have no more atmosphere. So we went from the phase where we had one object, Pluto, which had an atmosphere that we could study and argue about whether Pluto was going to lose its atmosphere or whether it was recent. We now have a whole slew of objects with different types, different evolutionary states of atmospheres, and we can understand these processes much better. I'm going to end with what I think is probably scientifically the most interesting object of the ones that was discovered, and that's the object Sedna. And Sedna is actually much like the earlier Kuiper Belt objects that were talked about. Sedna is so far away that we actually don't know much about it. And so what's interesting about Sedna is just its orbit. Let me show you what its orbit is. First off, here's one of these plots that you've seen of where objects in the Kuiper Belt are: Jupiter, Saturn, Uranus, Neptune, all Kuiper Belt objects all throughout here. Sedna is out there. And when we first found Sedna, we were pretty excited because we thought maybe this is the elusive new planet we've been looking for. Maybe it'll have a circular orbit around the sun. Or maybe it's just going to be one of these scattered objects like Dave was showing that's going to come back into the solar system. So we followed its orbit for a few months, went back, found old data, and it turns out that the answer is it's none of the above. Its orbit does this instead. It's actually nearly at its closest point to the sun right now, and it has a 12,000-year orbit around the sun before it'll come back again. But it never comes very close to the sun. The closest it ever comes to the sun is 76 AU. If you remember, Neptune is at 30 AU. It never comes close to Neptune. To get an orbit like this, you can't form on an orbit like this. Objects in the solar system form on circular orbits and then have to be scattered. How can you get scattered? When you get scattered by something like Neptune, you can be scattered out to an orbit like this, but then you have to come back to Neptune. This object is telling us with quite good certainty that something else in the solar system scattered it somewhere along its path. Something has to be there. So what could that something else be? This is what it should look like, but it doesn't. What could that something else be in the solar system? We don't know. The reason we don't know is because right now there's still only one Sedna. There's only one object like Sedna. Sedna is in many ways like Pluto. Pluto was sort of the sentinel that should have told us that there's a Kuiper belt out there if we were willing to listen. Then it took 60 years before we were willing to listen. Sedna, I'm hoping that we're willing to listen. There's a huge population out there. We need to find them. When we do, we'll be able to tell this tale of what Sedna's saying. Here's what I think is the most likely explanation, but we can't prove it yet. So if Sedna started out as a regular scattered Kuiper belt object, notice that it comes close to Neptune here, regular scattered Kuiper belt object, and then sometime in its history, let's see, go back to here, sometime in its history, a star came screaming by out here, that star would change its orbit. That star would change its orbit to look like this, and it would be the object that we see now. Now, why would there be a star close by? Well, if you remember back in Dave's talk, we think that the sun would have formed in a cluster of stars. So there would have been other stars close by back 4.5 billion years ago when the solar system formed. If this is true, and if we can find more objects like Sedna, what I find very exciting, first off, when we find more objects like Sedna, there are many different ideas for what could have caused Sedna, but I'm going to focus on this one. Each idea on Sedna predicts a different pattern of objects out there. When we find more objects like Saturn, and if this cluster birth idea turns out to be true, what we're looking at is a fossil record of not just the early solar system, but the birth of the sun itself. We have geochemical ways of trying to understand how the sun formed, but we have no way of looking at the solar system in an astronomical way and really trying to go back to those earliest times until now. These objects like Sedna are so far away, nothing touches them, they don't get perturbed by planets, they don't get perturbed by stars. We have this beautiful fossil record. If we can just find more of those little fossils to put together the whole story, we'll be able to tell the very sun of the birth of the very tale of the birth of the sun. For now, because we only have one, we can only put together a little bit of that story. But what we know for now is if it's true that the sun formed in a cluster and that's what led to Sedna, we can already start to tell a little bit about what that cluster was like by where Sedna is in its orbit. And it's like a nearby cluster of stars. Here's a forming group of stars, similar to the model that Dave was showing. And this is too many stars. If you have too many stars, you form too many objects like Sedna too close. We haven't found them. So you couldn't form in here. In this cluster, we would have formed right out here on the outer edge. It's not a bad place to live, to be born. Out on the outer edge of cluster, you have your supernovae occurring further out. We don't know that this is exactly the right analog yet, but again, we're continuing our search in these more and more distant regions in the solar system, and that's what we hope to be able to do to continue to tell all these tales from the outer solar system. Thank you very much.